Welcome back to the Deep Dive. Our mission, as always, is pretty simple.
We take the most complex research papers out there,
Ones that, make your eyes glaze over.
and we boil them down. We give you the essential knowledge you actually need to have.
It's the intellectual shortcut, really. And hopefully we have a bit of fun along the way.
Hopefully.
Today, we are taking a deep, deep dive into the mind of the large language model.
Mm-hmm.
Specifically, we're tackling what I think a lot of people consider its most powerful, maybe most magical, and definitely most mysterious feature.
In context learning, ICL.
Exactly.
And it really does feel like magic. I mean, if you've ever used ChatGPT or, any modern LLM, you know this feeling.
Oh, intimately.
You give the model just a couple of examples in the prompt, maybe say a few pairs of an input and an output to define some new task.
And it just gets it.
Instantly, without fail. The model adapts, it learns the new rule, and it can apply it to something totally new right away.
We call that few-shot prompting. And it is, it's just extraordinary when you stop and think about it.
It is.
Because traditional machine learning, that takes massive training cycles.
Right.
Days, weeks, updating billions of parameters, the weights, just to learn one new thing.
But with ICL, the LLM learns a new task in, the blink of an eye, all during what we call the forward pass.
And that's the fundamental paradox. That's the real puzzle we have to solve today.
Mm-hmm. How can a static network, a model whose weights were frozen solid weeks or months ago, how can it learn anything new?
Because learning by the book means updating those weights with gradient descent.
Right, but ICL seems to just bypass that whole process. It's a kind of computational alchemy. And today, we're going to break down the specific algorithms the transformer has apparently invented internally to pull this trick off.
So our mission is to understand the algorithmic mechanisms. We want to go beyond the simple idea that it's just finding a pattern or looking up data.
We want to know what deep mathematical processes, what kind of internal computer program is actually running inside that transformer architecture when you feed it a few examples.
We're basically synthesizing the absolute cutting-edge work here.
Yeah, from fields like mechanistic interpretability, theoretical computer science. We're trying to uncover how those fixed weights of the transformer can somehow encode the rules for a temporary adaptive learner.
Okay, let's unpack this. I really want to know if these models are secretly running code in their heads.
And if that code is something we'd even recognize.
Right. So let's start with the most obvious explanation. The one I think everyone, myself included, jumps to at first.
The simple one.
The simple one. When I give the model, say, 3 examples of converting English dates into a French format, and it gets the 4th one right, my first thought is, okay, it's just seen this exact task thousands of times in his training data.
It's just a sophisticated copy-paste.
Exactly. It's just looking up the answer based on, statistical probability.
And that's the crucial baseline misconception. It's an understandable one because LLMs are brilliant at statistical matching. But the research has shown pretty conclusively that ICL is way more robust and profound than just data retrieval.
So how do we know? How do researchers prove it's not just memorizing?
Well, they tested on things it could not possibly have seen before.
Like synthetic tasks.
Exactly, synthetic tasks. Imagine you train an LLM on normal English text, right? Then you give it an ICL prompt using completely made-up words.
Gibberish tokens.
Gibberish tokens that have never appeared anywhere in its data. And you define a simple rule between them. You say, for instance, that token A now maps to token B, and token C maps to token D.
So you're inventing a secret temporary language on the spot.
You got it. And when you then give it a new query with a new pairing of these nonsense tokens, the model can often correctly figure out the abstract rule.
The relationship you just defined.
The one you just defined in the prompt. It can apply it successfully. Now, if it were just memorizing, it would fail completely. It has no statistical history for those tokens.
So the fact that it succeeds proves it's adapting its internal function. It's not just pulling a stored answer off the shelf.
You've hit the nail on the head. It's not learning the task itself during the forward pass. It's applying a learned process for adaptation. It's learning how to learn.
And that process is what we call meta-learning.
That's the term. The huge initial pre-training phase, predicting the next word across the entire internet, it didn't just teach the model about language. It implicitly taught the model a recipe book.
A recipe book for how to solve new problems fast, with just a few examples.
Exactly.
So that distinction is so key. The weights are fixed, but the way the weights process the incoming prompt is flexible.
And that flexibility is the whole game. This adaptation, this meta-learning, it brings us straight to a really fascinating concept called MESA optimization.
Mesa optimization. Okay, that sounds like it's straight out of science fiction. Let's define that really clearly.
In a nutshell, it's a phenomenon where a trained model, like an LLM, implicitly contains an inner optimization loop.
An inner loop.
Yeah. The model itself, using its fixed weights, is running a learning algorithm, a little mini optimizer on the fly just for your prompt.
Okay, so just to be clear, the whole LLM was trained using a big outer optimization process. That's the normal gradient descent we always talk about.
Right.
And you're saying that within that final frozen network, a smaller inner optimization process has just emerged.
Precisely. Think of pre-training as this vast, evolutionary pressure kicker. The model's only goal was to get better and better at predicting the next word.
The highest possible score.
And to get that score across all this messy, structured, varied tests on the internet, the network figured out that the best strategy wasn't just to memorize patterns.
It was to build a subsystem.
An internal optimizer, one that could adapt really quickly to whatever local context it was seeing in the prompt.
So the training accidentally built a small, fully functional mini computer inside the network. And that computer's only job is to learn from the prompt.
And that internal mechanism is the MESA optimizer. The fixed weights of the transformer, they encode the rules of this internal optimizer. When your few-shot examples come in, that optimizer it activates. It calculates what adaptation is needed, and it stores that result temporarily.
In its own little working memory. This is it's absolutely fascinating because it forces a total rethink of what a neural network even is. It's not a lookup table. It's a machine that learned how to write its own temporary code.
Yeah.
But that still leaves the big question. If it's running an optimizer, which one? Is it some, bizarre alien thing we've never seen before?
Right.
Or is it something familiar?
And that leads us into the deepest and maybe the most surprising part of the research. It turns out the network didn't just invent an algorithm, it seems to have invented our algorithm. Okay, so this is the central kind of shocking claim in a lot of these new mechanistic interpretability studies.
Lay it on us.
The transformer architecture, just in its normal forward pass, can functionally replicate some very familiar optimization routines. And the most important one is gradient descent.
Whoa, hold on. Gradient descent, that's the foundational algorithm. That's what we use to train the entire enormous LLM in the first place.
The very same.
So you're saying the LLM runs a simulation of GD on the input prompt without changing its own billions of weights. That sounds like it should be computationally impossible.
It sounds impossible, I know, but the mathematical proofs are becoming really compelling. Researchers have shown, sometimes by literally building one from scratch, that you can configure a sequence of self-attention and feed-forward operations to perfectly mimic the algebraic steps of gradient descent.
So let's contrast this, just to be super clear.
Yeah.
Classical gradient descent is external. We calculate the error, we compute the gradient, and we update the global weight matrix. Let's call it $.
Right, the permanent weight.
But this implicit gradient descent is all internal. The big $. Is fixed, and the calculation happens inside the activations, adjusting the internal state, let's call it $, based on the prompt.
Exactly. The key difference is the locus of change. The learning is transient, it's temporary, confined just to that forward pass, and it only affects the next predictions in that one session.
Okay, so let's get into the weeds. How does a self-attention layer certainly become a gradient calculator?
Well, it comes down to what attention is always doing, right? It's comparing the current input to everything that came before it in the context.
Okay.
So when you structure that context as few-shot examples, say you're defining a simple line, $, mx plus b a ball, with 3 data points, the attention layers are basically built to spot the discrepancies.
So they see the input $, they see the correct outputs you gave it, and they see the model's own kind of naive first guess, young $.
And the difference between your dollars and its yeller, that's the error. That's the loss. The attention mechanism is using your examples as both the training data and the tool to calculate the update. It acts like a learned update rule. It looks at that error and it calculates an implicit gradient.
And that implicit gradient is then used to nudge the representations of the next tokens so the model can effectively adjust its temporary idea of what knowledge it should be.
And that nudge, that modification, happens through the residual stream, which is the information highway of the model. The core insight is that the attention layer's math is functionally equivalent to calculating the error and applying a tiny update to the model's internal parameters for the task. It's gradient descent, but running in milliseconds.
I have to push back a bit, though. I mean, Running even a few steps of proper GD is a heavy lift. Are we talking about a perfect by-the-book optimization? Or is this more like a messy, good enough approximation?
That's a critical question, and the consensus is that it's a highly efficient, learned approximation. Remember, the model didn't read a textbook on statistics. It discovered this mechanism purely because it was the best way to get the next word right. So the internal optimization is probably messy, it's probably weirdly parameterized, but it achieves the same end goal as classic GD, minimizing the error on the local task from the prompt.
So we should think of it as GD-flavored optimization.
Precisely. And we have really strong empirical evidence for this.
What's the smoking gun?
The smoking gun is when researchers test this on clean, objective tasks, like synthetic linear regression, where there's one right answer. What they find is that the predictions from the trained transformer closely match the output you'd get from running a few steps of actual textbook gradient descent.
Or even the perfect closed-form solution?
Or even the optimal solution, yeah. That convergence is the proof. The fact that the model's output lines up so well with a known mathematical optimizer, it confirms the attention mechanism is acting algorithmically. It's not just associating words, it's computing a solution. And this is why ICL is so robust. You can change the wording, change the format, but as long as the underlying function is the same, the model can often still find it.
Okay, this brings us to the next obvious question. And for me, this is central to the whole mystery. If the model is running this temporary optimization, where does it store the answer? If my little internal computer just calculated the perfect slope and intercept for this session, where does it write those numbers down so it can use them for the next prediction? Where's the RAM?
It's stored physically inside the transformer's guts, specifically in the activation vectors that are flowing through what's called the residual stream.
The residual stream, let's define that.
Okay, think of the transformer as a high-speed assembly line. Information comes in at the start and flows forward through all these different layers, attention heads, feed-forward networks, and so on. The residual stream is the central highway. It's the direct path that lets information aggregate and even skip layers. Every time a layer does something to the information, it adds its result back into this mainstream. It's the primary working memory for everything that's happened so far.
So it's the network scratch pad for the current prompt.
Exactly. And the research, using techniques like linear probes, shows that as the prompt examples get processed, the deeper layers of the transformer start encoding the results of that internal optimization directly into the vectors on that scratch pad.
And what are they encoding specifically?
For that same linear regression task, researchers found that the activation vectors in the later layers physically contain the weight vector. That is, the literal values for the slope and intercept, the learned dollars of the model, it just fit to your examples.
Are you kidding?
No, you can literally probe the stream, pull out that vector, and check it. And it matches the statistically optimal parameters you would have calculated yourself.
That is it's phenomenal. It means the model isn't just following a rule, it's deriving the rule and then writing it down for itself to use. But you mentioned something even crazier earlier, the second moment matrix.
Yeah.
Why is that a big deal?
So that detail is crucial because it speaks to the sophistication of this internal optimizer.
Okay.
Basic gradient descent just uses the first derivative, right? The slope of the error. But more advanced optimizers, like Newton's method, use information about the curvature of the error landscape, the second derivatives, to learn faster and better.
And that curvature is captured by the second moment matrix. It tells the model how steep the curve is.
Exactly. And the fact that researchers found evidence of the second moment matrix being encoded in the hidden state suggests the internal optimizer isn't just plain vanilla GD. It might be a much more efficient, meta-learned version of a more advanced optimizer that knows how to adapt its learning rate based on the task structure.
This is the complexity is staggering. So to recap, the model sees the examples, runs an implicit, highly tuned GD through its attention layers, and then stores the final answer, the weights for the temporary task, inside its own neural state.
All before it generates the very next word.
It's the ultimate form of temporary adaptive memory. It makes the model unbelievably powerful. Okay, so the optimization view is incredible. It explains the how. It's the mechanism for updating and storing the temporary learning.
It is the engine.
It's the engine, but it doesn't quite explain the why. Why does the model choose to adapt in one specific way over another?
Right. Why one rule and not a million other possible rules?
And this is where that other perspective, the statistical one, comes in. Bayesian inference.
Yes. If MESA optimization is the engine running the car, you can think of the Bayesian view as the GPS that's guiding the engine. It's telling the model the most probable, the most optimal strategy for adapting.
So how does in-context learning become a Bayesian inference problem?
We have to zoom back out and think about the pre-training data again. The whole internet. We often think of it as just a giant pile of tokens, but it's not. It's text generated by a huge, hidden set of rules and domains and
And
structures.
those are the latent tasks, the hidden math client.
Exactly. NF uses the hidden concept. So if the model sees a bunch of poetry, the latent task MathKiller is writing a sonnet. If it sees a Wikipedia article, MathKiller is retrieving factual information.
So the training data is just a mix of millions of these different latent tasks. And by training on all of it, the LLM learns the overall probability of seeing any given task.
Mhm. Now, when we give it a few shot prompts, say 3 examples of translating from Spanish to Portuguese, what are we really giving it?
We're giving it evidence, 3 data points.
3 pieces of observed data. And the model's goal, acting like a good Bayesian, is to figure out which latent task, MathCal, was the most likely one to have generated those specific examples. It computes the posterior distribution.
So PMath prompt examples, the probability of the task, given the evidence.
Right. Let's use a detective analogy. A crime happened. The possible criminals are all the latent tasks. The F. King Afkaf. The 3 examples you put in your prompt are the clues at the crime scene.
Okay, I like this.
The model, our detective, doesn't know for sure who did it. But based on those clues, it can assign a really high probability to the most likely suspect, say, Spanish to Portuguese translation.
And it can assign a near zero probability to MathCalc writing a limerick.
Exactly. The prompt examples just prune this enormous space of possibilities down to almost nothing.
So the LLM is inferring the rule first. It locks on to the most likely MathCalc file, and then it applies that rule to predict the output for your actual query. It guesses the function before it runs it.
And this makes the LLM a highly efficient Bayesian predictor. It goes so far beyond simple token matching. If your prompt has examples of some complex math function, the model doesn't just see numbers. It infers that MathCal's mathematical function fitting. It finds the most statistically likely interpretation of your input, and it uses that to guide its prediction.
It perfectly explains the power of few-shot learning. If you do zero-shot, you just say, translate this. The model has to guess the task from that one sentence, which is super ambiguous.
Highly ambiguous.
So with 3 examples, you're giving it concrete evidence. It can lock on to the correct MathCal almost instantly. You're narrowing that posterior distribution way, way down.
That narrowing is the whole statistical magic of ICL. You're giving the model just enough data to move its belief about the task from a vague guess to a really specific, confident prediction.
This view also seems to explain the scaling laws we see all the time. We see that making models bigger often leads to these huge jumps in few-shot accuracy, even if the overall training loss doesn't change that much. Why does more capacity make ICL so much better?
It connects directly to this Bayesian framework. The underlying theory says that the best possible learner is one that can accurately calculate this posterior probability. A small model can only do a rough, crude approximation of that.
But a massive model with hundreds of billions of parameters
Has the sheer capacity to be a better, more accurate approximation of that statistically optimal Bayesian learner. It can represent the incredibly complex dependencies you need to make good inferences across millions of potential tasks.
So more parameters doesn't necessarily mean smarter in a human way. It just means it's a better statistician.
It's a much, much better calculator for that high-dimensional posterior distribution.
What's really fascinating here is that these two views, the optimization view and the inference view, they aren't fighting each other.
Not at all.
They're like two sides of the same coin. The Bayesian part defines the goal. Find the most probable underlying task, MathCalc pass.
And the MESA optimization part defines the mechanism. Run an internal GD to tweak the internal state to actually execute that inferred task.
They're completely inseparable. The model runs the optimizer because the Bayesian inference told it what target it needed to hit. Okay, so we have the high-level concepts down. We have the engine, which is the implicit GD.
And we have the GPS, which is the Bayesian inference.
Right. But a transformer is still a physical thing. It's made of attention heads and feed-forward networks.
Yeah.
So how do these abstract ideas, the inferred task, the internal GD, how do they actually map onto the nuts and bolts?
Yeah, where in the network does this stuff actually happen?
Let's drill down.
So we can map this onto basically 2 different but cooperative low-level mechanisms. First, creating abstract representations of the task, and second, doing simple pattern copying.
Let's start with the abstract part. If the model runs its internal GD and figures out the right parameters for the task, How does it condense that whole complex rule into something you can actually use for the next token?
This is where we get the idea of task encoding via function vectors.
Function vectors.
Yeah. Research has found that certain attention heads, usually deep in the network, have specialized. Their job isn't to predict the next word directly. Their job is to create a compact summary vector that represents the entire task it just figured out from the context.
So they're like little data compressors.
Exactly. Imagine your prompt defines a really complex mapping. It needs translation, plus summarization, plus a change in tone. Instead of having to carry all those intermediate calculations forward, these special attention heads distill that entire complexity, the inferred task and the GD parameters, into a single, neat vector, the function vector.
That is an incredible amount of compression. You're saying the model can encode the entire complicated task into a single point in vector space.
And that vector is the physical manifestation of the temporary learning. And here's the crucial part. Once that function vector is calculated, it gets applied globally. It propagates through the residual stream and acts as a conditioning signal for all the subsequent prediction layers.
So every single token the model generates after that is influenced by this custom-made function vector. So when I tell an LLM from now on, speak like a pirate, the model is running its optimization on that instruction. It's calculating the pirate function vector, and then every prediction it makes is conditioned by that vector.
That is a perfect functional analogy. That function vector holds the style, the tone, the rules from the prompt, and ensures the model stays on task for the rest of the conversation.
Okay, that covers the deep, abstract, clever part. But what about the simple stuff? What about tasks that are just exact repetition?
Good question.
If I give the model a sequence like A, B, C, D, E, then ABC, I just need it to output D. Is it really running an internal gradient descent optimization for that? It seems like overkill.
It would be total overkill, and that's where we differentiate between that high-level abstraction and a much lower-level, simpler mechanism, the induction heads.
Induction heads. This was a huge finding a couple of years ago. They're often talked about as one of the first really interpretable circuits we found in transformers.
They are, and they're crucial.
So what do?
They basically implement a really effective find and copy rule. They are specialized attention heads that are just looking for two things in the context.
Okay.
A repeat token and the token that came right after that repeat token the last time it appeared.
Let's walk through an example. Let's say the prompt is the cat sat, the dog ran, the...
Perfect. The model needs to figure out what comes after that third dot. An induction head sees that the token that has shown up before.
Right.
So when it's processing the current position after the third the thought, its attention mechanism looks backward. It sees the first dot was followed by cat. It sees the second that's followed by dog.
So it knows the pattern is followed by something.
And its simple, hardwired by training rule is to find the token that followed the previous occurrence of the current token.
So it looks back to the dog.
It attends back to the dog token, which followed the last the, and it essentially copies the probability for dog forward to the current position, so it predicts dog.
It's building a temporary little association rule. If A was followed by B last time, then A should be followed by B this time.
Exactly. It's a mechanism for completing context-specific loops, and it's absolutely critical for keeping things coherent in long lists, Q&A pairs, dialogue, anything with a repetitive structure.
So they provide the basic sequential memory.
Absolutely. And you tend to find these induction heads in the mid layers of the network. They provide this foundational pattern matching ability. And then the deeper layers can build on that coherence to do the more abstract stuff we talked about, the GD and the Bayesian inference.
So it's not one thing. It's a whole hierarchy of learned algorithms.
A very sophisticated division of labor.
You've got the induction heads in the middle doing robust pattern copying. Then you've got the deeper layers running these complex emergent algorithms to distill abstract rules into function vectors.
And all of it was discovered organically by the model just because it was the best way to get the highest score on next word prediction.
It makes prompt engineering feel a lot less like magic.
And a lot more like you're designing a temporary curriculum for a tiny computer inside the machine.
Okay, so we started this deep dive with a pretty big mystery. How can a static network learn?
Right.
And I think we have the answer, or at least the beginning of one. It learns by running a temporary internal optimization loop. We know LLMs can run a version of gradient descent internally.
We know they approximate Bayesian inference to figure out the best task to perform.
And they compress these complex rules into single, usable function vectors using specialized parts in the network.
The big takeaway, really, is that these LLMs are fundamentally adaptive meta-learners. They are not just glorified autocomplete.
Let's just pause for a second on that word, emergence, because this is where the conversation shifts from pure engineering to something, well, something more profound.
It is the most crucial point. The one thing you have to hold on to from this whole conversation is that none of these complex algorithmic capabilities were programmed into the model.
We didn't write a line of code that said, when you see examples, start running an internal quasi-Newton optimizer.
We absolutely did not. The model's sole singular objective during pre-training was just predicting the next word in the sentence. That's it.
Maximize accuracy over a huge, messy data set.
And the ability to implicitly run GD, or to infer a posterior distribution, or to invent the induction head mechanism that is an emergent behavior, the network discovered it on its own.
Why?
Because it turned out to be the most efficient and effective pathway to solve that next word prediction task perfectly. To do well on a corpus that's filled with millions of hidden tasks, the network had to figure out a general strategy for adaptation.
And the solution it found was to embed a learning algorithm within itself.
The sheer complexity of the training data forced the transformer architecture to realize its full, inherent potential as a meta-learner.
Which confirms that the architecture itself, if you give it enough scale and enough diverse data, is inherently capable of this kind of optimization and inference.
It became an on-the-fly learner not because we told it to, but because that was the path of least resistance to its goal.
If we connect this to the bigger picture, ICL is maybe the clearest proof we have of these deep adaptive abilities just emerging from a simple objective.
It's a window into what these networks are capable of inventing when put under pressure.
And for you, the listener, I think understanding that an LLM is a meta-learner running an internal optimizer, that has to change how you interact with it.
It really should. Your prompt is no longer just an input, it's a miniature training set.
So when you provide 3 really good examples of a format you want,
You are literally kicking off a tiny internal optimization phase where the model is calculating the temporary parameters it needs and encoding them into its working memory.
so prompting goes from being a guessing game to being a form of temporary internal curriculum design.
Exactly. The quality and the diversity of your few-shot examples directly control the quality of that inner optimization loop. Bad examples lead to a bad internal optimization.
And a poorly constructed function vector.
The better you define the task for it, the more efficiently it can figure out what you want and encode the best parameters for that session.
This has huge implications for the future, right? If we can really understand these emergent internal algorithms, maybe we can design prompts or even architectures that actively leverage them.
We could optimize the meta-optimizer itself.
Moving from just watching emergence happen to actively steering it.
That's the goal.
So in-context learning,
Mhm.
it's so much more than just pattern matching. It's this complex dance of implicit optimization, Bayesian reasoning, and specialized neural circuits.
All happening layer by layer, triggered entirely by the specific tokens you put in your prompt.
And this whole conversation about emergence, about the network inventing on its own the very mathematical concepts that took human centuries to formalize, it leaves us with one final, very provocative thought. Go ahead.
Well, if optimizing for something as simple as next word prediction naturally leads a big complex model to invent its own versions of gradient descent and Bayesian algorithms that we recognize and can analyze,
Right.
what other currently undetected or maybe even novel algorithms might be emerging inside these scaled networks right now?
Algorithms that are critical for performance but are completely alien to our way of thinking.
Exactly. Are there completely new inhuman learning mechanisms already operating inside these models that we don't have a name for, we don't know how to measure them or even what to look for, simply because they help get that prediction score just a little bit higher?
The most powerful mechanisms might be the ones we haven't even found yet.
It's a chilling thought, isn't it?
It is a thought to chew on, and maybe a topic for a future deep dive. The mystery of the LLM mind just keeps getting deeper. Thank you for joining us on this journey.
We'll see you next time.
Goodbye.